Welcome to this course on reinforcement learning. In this lecture, we'll discuss what are called multi-arm bandits. Multi-arm bandits are a special case of reinforcement learning framework. They're special case because in general we'll have multiple states and actions that are possible in a RL problem, right? But in this special case called multi-arm bandits, we have only one state, so that's why it's called a special case. Although this has only one state, this is very useful and it has good applications in systems like recommendation systems and ad placements and medical trials, and also in wireless networks like cognitive radios, etc. So in this lecture, our target is to understand what is this multi-arm bandit framework, and we'll also learn a particular algorithm for solving this multi-arm bandit problem. So, consider a scenario where there are three lottery missions like this, and uh, assume that there is some arm which you can pull in each of these lottery missions. And whenever you pull a lottery mission, then you will get some random amount of money. Now, there are three such missions, and you do not know which mission is good, in the sense that which mission will give you more amount of money, right? Because as you know that in the case of a lottery, you will not get a deterministic amount of money, right? Sometimes this mission might give you a better reward, sometimes this mission might give you a better reward, and sometimes this. So these rewards are actually generated from some underlying reward distribution, uh, which is not known to us. So whenever you pull a uh, lottery mission, there will be some underlying reward distribution from which the money that you get will be decided. If someone gives you these three reward distributions, then we can, if we have access to the reward distribution, let's say we call it as px of x, then we can easily calculate what is expected value of x, because we know the pdf. We can easily calculate what is the expected value of reward that you can get from each of these missions, and from that you can understand on an average which is a better mission to stick to, right? So if you know that, then your job is easier. But if you do not know which mission has a better reward, then there is a dilemma, right? uh, so here the actual problem that we have to solve is, let's say we are given t chances to pull these arms, and in each chance you can decide whether you want to pull the first mission or the second mission or the third mission. And in every of these chances you can change your choice. For example, in the first choice you can pull arm 1, and in the second choice you can pull arm 3. You can decide which arm to pull in every chance. Like, what is our goal? Our goal is to maximize the total reward that you get in all these t rounds. So this is the multi-arm bandit setup. So this multi-arm bandit setup suffers from a problem called exploration versus exploitation dilemma. So what is exploration versus exploitation dilemma? Let's say there are three bandit missions that you have, or three lottery missions that you have. Let's call them A, B, and C. And let's assume that we are given some 100 chances to pull these arms. Now, the goal is you want to maximize the total amount of money that you get in all these 100 chances. So what is the issue that we'll face? Right now we don't know whether mission A is good or mission B is good or arm C is good. So which of these arms is good is not known to us. So what should we do initially? Can you think of a strategy to make the best use of these 100 chances? One typical idea that we'll get is, since you have 100 chances and you don't know which of these three arms is a good arm, what anyone would typically try first, you have 100 chances. Let's say maybe you use first Let's say you use the first 9 rounds to explore uh, each of these arms. So maybe you'll pull arm A 3 times, and you'll pull arm B 3 times, and you'll pull arm C 3 times. Based on what you get in these 9 chances, you can roughly understand how good each of these arms are, right? Let's say you got some 5 rupees when you played A for the first time. Since it's a random amount, right? Again, if you pull the same arm, you might not get the same amount of money. So maybe you'll get, let's say, plus 3 in the second time, and the third time, let's say you got plus 1. So, on an average, how much money did we get in these 3 rounds? It's 5 plus 3 plus 1 by 3, which is, if I denote it as mu bar of A, that is 3, right? This is the average that you got. It's 9 by 3, which is 3. Similarly, let's say you pulled these arm B 3 times, and you would have got some reward in each of these 3 times. So let's say that average turns out to be 4. Similarly, you pull arm C 3 times, maybe you'll get 1, 5, and let's say 7. So what is the average? 8 plus 5 by 3. So which is 14 by 3. So that will be your mu bar of C. So which arm has a higher sample average? From these examples, we see that this arm has a higher sample average. So from whatever experiments or whatever exploration we have done, now we can understand that arm C looks like the best arm. So one strategy or one simple algorithm could be, you do explore each arm for a few times, and based on that you decide which arm has the highest sample average. And for the remaining rounds, this is what you did in the first 9 rounds. For the how many rounds are we left with? We have still 100 minus 9 rounds, which is 91 rounds are left with us. So what do we do in these 91 rounds? Based on whatever we have explored, we thought that arm C is the best arm. So we'll keep pulling arm C for the remaining 91 rounds. So this is what is called a famous algorithm called explore first, then commit, which is also called as ETC. So what is explore first then commit? You explore out of the total rounds that you have, you explore for few rounds, and based on whatever data you have seen, you decide which is the best arm to pull for the remaining amount of round. That's what is called committing. Okay. So this is also called like exploitation, because you are exploiting the information that you learned in the first few rounds. So what is this dilemma of exploration versus exploitation? So how many rounds should you do this exploration, and how many rounds should you do the exploitation? Let's say in the exploration, what is happening? You don't know which is the best arm. So you have to pull all the arms. That is, you will pull both the good arms and the bad arms. So that is, if you explore too many rounds, that means you are playing the bad arms also a lot of times. So your overall reward that you get in this 100 rounds will be less if you do too much of exploration, because you're playing the bad arms also a lot of times. However, if you do very little exploration, so instead of, let's say, doing 9 rounds of exploration, I do only 3 rounds of exploration. That is, I'll pull arm A1, arm B1, arm C1, and based on these 3 samples alone, I will decide which is the best arm and play the arm for the remaining 97 rounds. What is the issue with this approach? Because these rewards that you get are random, right? So just based on one sample, if you decide which is the best arm, if out of luck some good arm doesn't perform well in that particular round, then you will rely only on that particular one round and do for the remaining 97 rounds. So your sample estimates that mu bars will be not very accurate. So you will have to suffer if you make a bad choice because of too little exploration. This is the trade-off that you have to take. How much exploration rounds you want to have and how many exploitation rounds that you want to have. So this is what is called the exploration versus exploitation dilemma. Now that we have understood what is ETC algorithm, let us look at it in a more formal way. So here we are assuming that we have k arms and we are having t rounds. That is the total number of rounds allowed is t. And what we are doing, we are first doing exploration. That is in the first n rounds. So what is the ETC algorithm? We'll first explore. So what are we doing? We are exploring each arm and play each arm n times. That is, if you have 3 arms A, B, C, and if your n is 2, then what will we do? We'll explore arm A 2 times, arm B 2 times, and arm C 2 times. So this is the first step. So explore each arm n times, and then what are we doing? You compute the sample average of the rewards that you got for each of these arms. Here I am using the notation AT is the arm that you are picking at round T. Okay, so you just take the sample average of each of the arms that you have played during the exploration, and based on these sample averages you commit. That is, for the remaining, how many rounds did we explore? Each arm you are exploring n times. Totally you have k arms, so kn rounds you are exploring. So for the remaining t minus kn rounds, you are committing to the arm with the highest sample average. So you have got based on mu bar of A, mu bar of B, and mu bar of C, you will see which arm has the highest sample average, and you play that arm for the remaining t minus kn rounds. So this is the explore first, then commit algorithm. So how do we measure the performance of this algorithm? That is, how good is this algorithm doing? So we, like, if we denote RT as the reward that you get in time t, so this is the total expected reward that your algorithm will get in all the t rounds put together. And to just understand how good is this algorithm, if someone had given us what is the best arm already, that is, someone had told you even before doing any exploration that arm A is the best arm, what will you do in that case? You will pull arm A for all the t rounds, right? Because you already know that arm A is the best arm. So what is the best reward that you can get in such a case? So mu star is the best arms reward. And if you pull arm A, like if you pull that best arm in all the t round, then the reward that you'll get will be t into mu star. So we are just comparing with this. This is the maximum reward that you can get, right? Because you're not wasting any slots in exploration, because someone has already told you that arm A is the best arm. So this is the best reward that you can get, t into mu star, versus what your algorithm is getting. So this is what we call as regret. This is the regret of not knowing which is the best term. So any algorithm's performance is measured based on this quantity. So if you have two algorithms and you want to understand which algorithm is doing well, you plot this value for both the algorithms and see whichever has less regret, then that is algorithm is a better algorithm. And what is interesting to understand is what is a good value of n to use. That is, how many times we should explore. So in the next lecture, we will do a rigorous analysis of what is the regret of this ETC algorithm and what is a good value of n to choose. So this is about the multi-arm bandit setup and a very basic algorithm called ETC algorithm. Thank you.